This content is produced by Darknet Breaker, a cybersecurity and dark web education brand. All videos, posts, and content are strictly for educational and awareness purposes only. We do not promote, support, or encourage any illegal activity. Our mission is to expose digital threats, protect online users, and educate the public about cybersecurity risks in the modern world. Stay ethical. Stay protected.
In a traditional chatbot interaction, a compromised prompt might result in a toxic response or a data leak. In an agentic environment, that same prompt can trigger a wire transfer or modify a production IAM policy. This architecture relies on three components: user input, the LLM reasoning engine, and a set of actionable tools. The system is designed so that natural language instructions from the user are translated into API calls that interact with the physical or digital world. This setup introduces the risk of excessive agency. Attackers target the agent's privilege level by crafting inputs that the agent interprets as valid instructions for its own tools, performing the requested action on the attacker's behalf. Connecting agents to these tools provides the functionality teams need, but it also creates a direct, unmediated link between untrusted natural language and sensitive system operations. GitHub agentic workflows allow developers to automate repository management using instructions written in Markdown. To perform these tasks, the underlying agents are often provisioned with broad, cross-repository read permissions. The Git lost vulnerability exploits this setup. An attacker places malicious instructions inside a public GitHub issue. When the workflow triggers, the agent reads the issue and uses its personal access token to query a private repository. Because it treats the issue body as instructional data, the agent obeys the hidden command, extracts the private vault's contents, and posts them as a public comment. In this environment, the context window is the attack surface. Reading untrusted data while holding high-level credentials creates a path for the agent to unintentionally leak the very data it was meant to protect. These risks compound in multi-agent systems. Here, a frontline agent, like one handling customer service, processes external inputs and passes information through a trusted internal channel to a privileged back-end agent. This enables agent-in-the-middle attacks. By manipulating the message in transit, an attacker can embed hidden instructions. The system treats the message as trusted because it originated from a peer, bypassing standard capability checks. This is why the MITRE Atlas framework categorizes these exploits under LLM plugin compromise and privilege escalation. The attack doesn't rely on a code-level bug. It relies on the back-end agent's failure to verify the intent of a peer's request. Consider the standard defense, network encryption. If you implemented perfect TLS between these two agents, would that prevent a payload-level manipulation? TLS only ensures the packet wasn't tampered with during transit. It cannot verify that the semantic content inside the packet is safe. The back-end agent still receives and executes a perfectly encrypted, yet malicious instruction. The risk is not limited to real-time prompts. It also exists in the supply chain, specifically in the model registries, where teams download open-source models for their automated pipelines. On platforms like Hugging Face, an attacker can use namespace hijacking. When a developer deletes an account, an attacker registers that same username and takes over the established model directory paths. Corporate servers configured to pull from that path will unknowingly download a poisoned model. Once loaded into the pipeline, it enables remote code execution. This demonstrates that an agentic architecture can be fully compromised at the source before any user ever sends a single message to the system. To defend against this, we must separate capability from authorization. A governance layer must verify the specific intent of the current task. We also implement out-of-band hash chains, cryptographically verifying the intent in a separate process before the action clears. This defines the secure architecture. First, validate the intent of requests. Second, implement zero trust between agents. Third, explicitly pin your supply chain. Using past trusted network assumptions in an agentic system leads to cascading failure. Resilience requires enforcing cryptographic zero-trust boundaries at every step of the reasoning loop.